So it's great to be here. Oh, I have a lapsed time already. That's not a good sign. Let's start over so I have fresh time, because I need all 40 minutes. It's actually really, really exciting to see such a vibrant and bright, exciting European community for Clojure. So this is really, really great. And I'm here to talk right now about what I've been doing in Clojure, and my second talk will be about the reducers library. So what I've been building with Stu and others is Datomic, and I want to sort of give you an overview of what it's about, why we made it, what problems I was trying to solve, what my answers to those problems were, and a little bit about our implementation of that in Clojure, and a brief summary. So the problems. In Clojure and Datomic together are trying to solve, the big problem, which is complexity. And while I was building Clojure, when I first started, this paper came out, and eventually I read it, and it was very inspiring. I was already working on Clojure, and I'd kind of decided to go the functional route, and this paper definitely inspired me to sort of stick with that. And in it, Mosley and Marks sort of describe a vision, not an implementation, but a vision for what less complex programming could be. And one of the cornerstones of it was functional programming. Another was declarative programming in the form of relational programming. But there was this magic component. They had correctly identified, I felt, that complexity is caused by state, or a substantial portion of our complexity is caused by state and control problems. And they described this system that you use functional programming and relational algebra to manipulate this data set. But then there was this magic, right? Things happened in your program, and somehow this data set was different. It's like a miracle occurred. And the part I think they left out, and what actually is the hardest part of solving the overall problem here, is closing the loop and really coming up with a solution for process. So that's one of the things we're trying to do. We heard a lot about logic-oriented programming, declarative programming, and evident programming. That's something I think is really important. I think Cascalog and CoreLogic are important things. And in terms of the data world, in the database world, we know, or we should know, that those languages like SQL, those declarative languages, are far better at manipulating data than, well, definitely than object orientation, but even than functional programming. They're another level up, they're set-oriented, they're further away from how, and more oriented towards what you want to do. But those languages and that technology is largely trapped in database servers. They have a lot of great technology that underlies SQL, for instance, but it's trapped in servers. However, most of those servers and most of those designs are what I would call place-oriented. We heard the term, current-oriented or current state-oriented, which makes it very difficult to write coherent programs, because at any point in time, you don't know what the basis is for your logic. The other big problem with databases there are many problems with databases being over there. And we've gotten so used to them, we think they're sort of inherent properties of databases. One was this no basis thing. The other is our fear of round trips. We're afraid to communicate with the data set, more than once. And a lot of that fear is based around overloading the server, and that's one of the concerns. But the bigger concern is consistency. Multiple round trips against a place-oriented server means things change between your questions. Now your questions don't have the same basis. And you really don't have the ability to talk about a value in the large, because things are moving away from you. And that causes you to do bad things in your program, right? We issue these queries where there's business logic that determines these are the entities we care about manipulating, and then there's like presentation logic that says I want to put this on a web page and show name and address and phone number. And we have to combine these what should be two independent sets of decisions into one query, because we're afraid of making we can't make two round trips and have the answers be coherent, which is bad. Another factor in the design is to try to leverage some of the new designs that have seen proof in practice, like in Dynamo and Bigtable, for distributed systems that have more scalability. And one of the questions I have is I see sort of this bifurcation. There are consistent systems with scalability issues and scalable solutions that have really given up a whole lot, a real lot, in terms of consistency and queryability and things like that. So is there a way to parse these things, pull these things apart, and get a different combination? Some distributed redundancy, but some consistency. Can we tap into elasticity somewhere, which is often not a property of either of these systems? Elasticity being, the ability to dynamically during, say, the course of the day, get more or less capability. But I think when people choose eventually consistent systems, they're taking on a boatload of complexity, and we're just starting to have people come back grumbling about how hard that is. So we're looking for flexibility, right? A lot of people move away from structured systems like SQL to something else in order to get more flexibility. And of course, we know data is not in rectangles inherently. Some of it's sparse, sometimes it's irregular. We have hierarchical data. We often have repeating attributes. All of these things imply a whole bunch of conventions in the relational model as realized in SQL databases that don't serve us well. So I think more flexibility in data modeling is definitely something that we want to have. And with that, it's not just like I wish it was easier to do whatever. There's a real complexity associated with structure, right? As you impose structural decisions in your representation of the data in your storage system or database, that ends up poisoning your application, making it difficult to change over time. And that's another pressure people feel about SQL databases. They say, ooh, I don't like them, and if you sort of tease it out, a big problem is over time, a large database built that way is extremely difficult to change. Another fundamental thing, of course, it's been a topic yesterday, is the fact that databases today generally do a very poor job with time. And, before we had computers, we had the term memory and records, and they meant highly durable things. It meant, memory meant remembering things, and records were things you kept, not things you kept writing over. And so I think we really need, in moving forward with information systems, to maintain information, and that means to maintain information about the past. Place orientation, whether it's in memory, right, which is objects, or on disk in the forms of update in place databases, is an idea whose time has gone. We have plenty of space now. And of course, there's so many practical uses of this besides the complexity reduction. The final thing we want to sort of accomplish as an objective of the system is to make perception and reaction sort of first-class things. These are often things that we try to bolt on top of a system after it exists, and we have to do polling and things like that. But I've made the argument before. Perception is largely a passive operation, right? Light bounces off of things, it bounces onto your eyes, and you're not working very hard to make that happen. And as a result, you want to be able to react. But in particular, you want to accomplish these things without polling and in a way that gives you a consistent view, right? Perceive means to take as a whole. So the answers, as evidenced in Datomic, are this. The overall model is that what we want to do is empower the application server. That means that we want to enable it to perceive things that happen in the world, the process of the business or the activity the system is being applied to react to that, to remember anything that's of use to the application, right? Remembering should be straightforward, to make decisions, and then to act upon those decisions. And when you do this, you realize you can actually put that much of the work in application servers, and when you do, you get a scalability property that's very useful. But it does require some coordination, right? Because if I want to look at the back of your head, 500 people can do that all at the same time. But if I want to be your barber, I actually have to go to your head at some point. So there has to be some coordination. So divvying this up is what we're trying to do. Now the state problem is an interesting one, right? We know we want to have values, but we're going to have novelty. So how do you have novelty and a value at the same time? And I think it's just by having a slightly more nuanced notion of what constitutes a value. What constitutes a value is something that any part of which you've already seen, you can go back to later, it will never be different. That definition doesn't preclude the thing that you're looking at in the whole growing, right? Like a tree. Oh, you probably can't even see this. Like the rings of a tree over time, right? You can get more layers on the outside of the tree. It doesn't affect the core of the tree. And so you can have this broader notion of the database as a value in which it's still immutable in spite of the fact that it's growing, because no part of it ever changes, right? The novelty is always accretion. And that's derived from the fact that the past doesn't change, so we just simply don't change it. And the only implication of it is that process, the activity of a business or whatever you're going to apply your system to, requires new space. New information, new space. New facts, new time, new things happen. Of course you should have new space. I mean, the fact that we think we should put that over what we already had is a goofy thing that's arisen from the fact that we used to program with really tiny computers. We have to move away from places. Another key thing in trying to pull this off is to realize that if you're not going to update things in place and you really do want to capture information, you have to reify process. You have to turn process into something that you can, that is a value, that you can store, move, communicate, and things like that. So you want to reify process, which means that you need to have some representation of novelty. In Datomic, we reduce novelty down very, very small. And the process is then merely reduced to the assertions and retractions of facts. I'll talk a little bit more about facts in a bit. And then everything else can be turned into that. We touted yesterday extensively the values of declarative programming. I won't go more into that except to say, I agree and have been pushing for that. In Datomic, what we do is we move query into the applications and we implement query using Datalog, which is similar to core logic, but it's not generative. It also is guaranteed to terminate and much faster for query because it has a set orientation. And we want this to be not a property of the database particular, but something that's a tool for the application developer. You should be able to apply declarative programming to anything, and Stu showed that yesterday. We have to deal with the over-there problem, and the first thing we have to do to solve that is to take things apart. In particular, we're going to move the data off of a privileged server to a storage service. And in that way, we say there is no machine that has privileged access to the storage, that has any better access to the storage than any other machine. Now, this is actually a property that's already arisen. Today, I mean, there was a paper recently that was something like disk locality considered irrelevant. And it is. It's the fact of the thing. The machine on which the disks reside is actually, like 1% better at processing the data that's on those disks than a machine on a fast network connected to that machine. There's no real privilege to having the disks. And there's a lot of problems with making privileged machines. We know we want to run on these giant suites of servers where machines come and go, and there's a tremendous amount of redundancy. So we don't want any privileged access. And that effectively will mean that all of the application servers become peers in solving any problem. They'll all have access to the storage. In terms of consistency and scale, the trick here is to separate reads and writes. As soon as you separate reads and writes, and so here we're not really talking about writes as overwrites, but separate novelty processing from historic processing. You get the ability to make independent decisions about those two things. And I think you also get to make two sets of consistency scale decisions. Because now you can say, what kind of consistency scale approach do I want to take for novelty, and what kind of consistency scale approach do I want to take for answering questions. And in Datomic, we choose transactionality for writes, which is a consistent system, and therefore more traditional availability properties and scaling properties, and immutability for reads, which means we can now start leveraging distributed systems that have highly scalable and high availability properties for that. In terms of addressing flexibility, the key to getting more flexibility in your data representation is not actually to trade tables for documents. You don't get more flexibility by using documents. Documents are very, very rigid things, right? It's easy to add something to the representation of the new documents you make, but the old documents you have are made out of concrete. They're much harder to change or manage than tables were. But better even than tables is to just remove even more structure and approach data in a way similar to the way RDF does. And the problem with RDF, which is like a subject, predicate, object system, is that it ignores time. And the better way to approach doing data, I think, is to step back and say, what are we actually doing in information systems? What is information? What does it mean to inform, right? Inform means to convey knowledge via facts. And what is a fact? A fact is something that happened. That's what a fact is. It's not a place, it's not a slot for where your email address goes. It's something that happened. And as soon as you say a fact is something that happened, you just play the game. What's a minimal fact? Sam. Not a fact. Sam likes. Not a fact. Sam likes pizza. Close, right? But Sam hasn't necessarily always liked pizza, and Sam won't necessarily always like pizza. So Sam likes pizza as of right now. Then Sam becomes lactose intolerant, and things change. So the minimal unit of a fact is entity, attribute, value, and time. And we represent time using transactions. I'll explain that later. But it's essential that you include time. You don't have information if you don't have time. So in terms of managing time, we do that by serialized transactions, right? There's a coordinator, and as you'll see, it serializes all the information. Every datum includes this transaction. Transactions are first-class things, so they are also facts. The fact that there was a transaction is a fact. And transactions themselves can have attributes, like, for instance, the time of day at which they occurred, or who did them, or why. And the result of this is that you can start talking about the database as of a point in time. Database can be treated as a value. The database at any point in time can be treated as a value, which is really what we're trying to achieve. And in terms of perception and reaction, we're going to push the process. The great thing about dealing with novelty separately and not polling is there's actually not that much novelty in a lot of systems. Most businesses don't double the amount of information they have every year. They have 10% more information each year than they had the year prior. So you just push the novelty out. And that means that you can see the novelty, right, inside any peer. And because the novelty has been reified, right, we said process is going to be turned into data, you can just query that data. So if you want to react to certain things happening, you're going to be informed about process, and you can query process and say, oh yeah, that was something I was interested in, let me go do something. In addition, because you can coordinate this novelty with the state of the universe, before and after, you can really accomplish any decision-making process you want. So let's look a little bit at the implementation. The architecture basically looks like this. Ooh, I have a thing. Can people see that little red dot? In the back they can, so in the front you have to too. So what we're going to do is we're going to deconstruct the traditional database. The traditional database does transaction processing. It stores stuff, it supports queries, and it does indexing. All this stuff is usually jammed into one machine or one logical cluster of machines acting in this role. And in Datomic, what we do is we split this apart. If we look at the bottom, the first thing we do is we say storage is something that's commoditized, and we're going to use a service to do that. And there's any number of services that you could use to do that. And we're going to say the application servers, these peers, are empowered. Right, we wanted them to be able to perceive things, make decisions, right, remember stuff. So in order to perceive things, they have to have live change be sent to them. And there's an index in memory that maintains novelty until such point as it becomes part of storage. There's a cache so they can remember things. So anything they've ever gotten from storage as part of their working set, they can remember. There's a query engine inside this peer library that you put in your application server that can issue queries, and a query is going to be always against this combined set, and I'll talk a little bit more about how we do that. This communication library is in there. There's a separate, and so this part is elastically scalable, right? You can pull up application servers and take them down. They can be doing different jobs, right? There's nothing about this architecture that says the data is specific to the application, right? You can have new applications that do new stuff and just add them to the mix. The data is not application specific. And then there's a separate component called the transactor whose job is strictly to do coordination. And I think I'd explain all these things in more detail later. So roughly we divide it up into transaction processing, storage, query, and memory. So what does it mean to have a database that is an immutable expanding value? Actually, how are we going to represent that? I think a critical thing is that, in my opinion, a database is something that gives you leverage over your data, right? So a file system is not a database because it really doesn't give you any leverage over the data. It's just like, give me a key and look up a value, and then I get my file. Well, guess what? Key value store is also not a database by that definition. There's no leverage there, nor is just raw dump of log-like event data. Again, no leverage, no indexing, there's no leverage. I can't find stuff. I really can't do anything except load it into something else that gives me leverage. So it has to be organized. So we want to take all this information, these atomic facts, organize them to support query. The organization you need is actually very simple. A sorted set of facts is sufficient to give you leverage over your information. And so that's what we do. Effectively, the entire system is oriented around providing all of your information as several sorted sets of facts. Now, Bigtable, the design of Bigtable, how many people are familiar with Bigtable, Google's Bigtable? All right, so the design of Bigtable and systems like it, I'm not sure Bigtable invented this at all, but Bigtable is an example of it, shows that live indexing, right, taking novelty and immediately trying to put it in storage in a leverageable way is not possible. It's not possible to do fast enough. Right? And a lot of in-place databases suffer from the scalability problems of trying to do that, right? When you commit against the SQL database, it's effectively in the indexes already before that returns. That's very expensive to pull that off. And any kind of database that tries to take everything that you say to it and put it on storage in an indexed manner is going to fail to be scalable and fast. So the Bigtable model is basically to commit everything that you encounter, right? Every piece of novelty gets stored, but the leverageable representation of it is divided up into two pieces. An index in memory, a sorted version in memory, which is where the very newest stuff goes, and then a sorted version in storage, right, which periodically has the stuff from memory merged into it. So you accumulate a big block of stuff in memory, then you merge it into storage. This empties out, you accumulate more, you merge it into storage. This accumulation in memory has nothing to do with durability. You could have been making it durable in a very efficient way as it comes in, just as a backup. But the leverageable representation is a combination of a live index in memory and a durable index in storage. So they do this with blocks. They have a big block, and then periodically they blow the block out to disk, and then processes merge those blocks to make bigger blocks. Datomic does not follow that model because we see a lot of value in trees, obviously, being immutable. So we do the same thing. We occasionally merge into storage, but both the representation in memory and the representation in storage are persistent trees. So Datomic is sort of durable persistent trees, or persistent trees. So storage really is divided up into, two separate parts. There's a log. Obviously, everything that comes in you have to put, if you want to be a real database, you have to put in storage right away if you want to be durable. So everything gets put into a log. Unsurprisingly possible in this audience is that that log is actually also a tree, which makes it easy to maintain and look up stuff later. But the leaves are append only. And then there are various covering indexes. And a covering index is an index that has everything in it. So it's not an index that points to something else. And so we maintain indexes, sorted sets of all the facts by entity primarily or by attribute primarily, which allows you to get different leverageable views of your information. In terms of the storage system, the storage service requirements, what we need from a storage service is essentially a key value store. What we're going to put in there is not the individual facts, but these segments of these indexes, big chunks. We treat key value storage as like a file system, right? We need two other things, though, to fully implement the model. And what was interesting in doing this design was that what you end up needing is the Clojure state model in an adorable way. And so the full state model, you need two other constructs to fully implement this. One is something like a ref, like an atom, and the other is something like a ref, but it also is an accumulator. And there's that word again, pods. And we call them pods. I don't want to talk about pods. So there are these two separate things, which you need to do. But the implications they have on the storage services, in order to implement atoms against storage, you need consistent read. And in order to implement pods in storage, you need conditional put. So if and so we can reside on top of any storage system that can do those two things in addition to key value. So an index looks something like this. I don't expect you to be able to read this, but the key point is it's this huge tree, right? The root index is a set of roots. It says that, this is the index as of this transaction. So it has everything that ever happened before this transaction, modulo history, which I don't have time to talk about right now. But there's an index for entity attribute value time, and one for attribute entity value time, and one for value attribute entity time, which is the reverse one, and then attribute value entity time, or transaction. That T is always transaction, and also Lucene we keep in here. Then there's a very high branching factor tree. It's always 3 levels, right? There's a root, there's a set of directories, and a set of segments. Each segment is a block, you can think like 64K-ish block of compressed, sorted datums. And it's those blocks that get put in storage. None of these things ever get changed. In other words, they get put in storage, they never get modified. They can be cached relentlessly and pervasively. So, a database value is a combination, okay? In memory, we also have an index. It's a new persistent sorted set with a high branching factor. So it's different from the red-black tree that comes in Clojure. With the high branching factor, and that memory thing and the pointer to the path to the storage on disk, which is behind a cache. So essentially, the database feels like it's looking at two things, a memory index and an index that's based off of a cache. It also feels like memory. That cache is a hierarchical cache. The tier closest to the application code is objects in the heap. The next tier is these blocks that have been pulled from storage but are being kept locally, but they're still compressed and then not yet been turned into objects. In this way, you can reference hundreds of millions or billions of things without crushing the Java heap, because you efficiently move between these two tiers of the cache. And the cache is dynamically backed with storage. So if you get a cache miss, it will go to storage and pull it. And so so effectively, you have a value. I mean, it feels exactly like a value. That's dynamically backed by I/O. There's no problem with doing this as long as what's behind the I/O is immutable. Right? This whole thing like I/O is this other thing, not for functional programming. It's not. This is I/O-driven functional programming. And then there's an object, a little struct-like thing at the top, a map that points to these things and some of the other things. And there is one atom. That's it. One Clojure atom to deal with the movement of this identity over time. So we talked about process being reified. Assert and retract are a sufficient primitive representation of what happened, but they're not a sufficient representation of what caused it to happen. So for instance, a transformation like I want to add $10 to your bank account is something that I could do by looking at your bank account and seeing, $1,000, okay, I'll just make a new fact that it's now 1,010. That's subject to race conditions. It's like two people trying to cut your hair at the same time, right? That's not going to work. And it's a simple fact, right? You can't cut people's hair remotely, right? This distributed, eventual, consistent, what's an eventual haircut look like? It can't be good. It can't be good. So you want these transformations to happen inside the transaction, and so we have these things called transaction functions, which again, for this audience, shouldn't be surprising, are functions of the database and some arguments. What they produce is not a new database. What they produce actually is new transaction data. So you're able to put in your transaction stream, assert this, assert that, add $10 to Sally's bank account, assert this, assert that. And what ends up happening is that function gets called, and the result of add $10 to Sally's bank account is it looks at Sally's bank account, sees if there's $1,000, and makes an assertion inside the transaction that Sally's bank account is now $1,010. At this point, no one else is in there, trying to cut your hair, and that's guaranteed to be atomic transition. So transaction data is one of three things. It's either an assertion, a retraction, or a call to a transaction function. And what the processing that happens inside the transaction is to expand these functions. So you can imagine a transaction with assertion is plus and retraction is minus, and then there's a call to the foo transaction function, and that expands into or returns a list of two other pieces of data, which is a call to bar and a call to baz, and each of those turn into two lists of data, which are more assertions and retractions. Eventually, it bottoms out to be all assertions and retractions. And this smells like what? Macro expansion, right? Macros expand until they're not macros anymore. Transaction functions expand until they're not transaction functions anymore. So they're only assertions and retractions. And then this whole set of information goes in, because now it's information. So the transactor accepts transactions. It does this expansion. It applies that. It will log the data immediately, and it will broadcast the change, like in that picture. Every now and then, it does this periodic indexing, right? It drains the memory index, merges it into the tree. There's structural sharing, again, on disk. All the things you're familiar with from the design and memory happen on disk, including the fact that this indexing job creates garbage, right? Some of the nodes in the tree are shared with the new index, and some are orphaned by that process. And so there's actually GC for storage, which should make perfect sense, right? It's not a different problem. It's the same problem in a different place. It's just we haven't taken this approach to that place yet. In terms of declarative programming, we embed data log, and Stu gave you a nice tour of that. It can take data sources and rule sets as arguments. I think that's very, very important, right? I think the notion of an ambient database is extremely challenging to support. And if you really want a first-class system, you need to have first-class data sources and first-class rule sets. If they're magical in some way, you will not end up with a programmable system. So it's fully programmable. You saw the extension to work with collections and to call your own code there. So we solved the over there problem by moving a lot of good stuff over here. Right? Now peers can directly access the storage service. They don't write to it, but they can directly read from it. They don't need to go to some master to do that, which means that your application servers are scalable. You can have as many of them or as few of them as you want. And behind that, you can have one of the newfangled key value stores with its own scalability and redundancy properties. And that activity can be highly parallelized. This will trounce any single server solution or clustered server solution you can come up with. They all have their own query engine. This is another thing. We've always been, the phrase long-running queries, like, ooh, beware. Now you don't care, right? Let's say you have a new part of your application, and there's going to be this analytics going on, and they are actually going to take a while to calculate. They need to manipulate a lot of data or do a lot of calculation. So what? You fire up a box to run that on. That box is churning away. Is it hurting anybody? No. It has its own brain, which is what you want. They have their own live merging system, right? So the same thing that happens in the transactor happens in every peer. They accumulate novelty, and they have access to the storage, and they merge live when you issue queries. And every now and then, the transactor will say, you know what? I've merged all that novelty into storage. You can drop it from memory and just use the new root of the index tree from storage. And then they have the same process happens there. And I talked to you a little bit about this two-tier cache, right? There are the segments that are fresh from the storage that are not yet on the heap as individual objects. And then there are the full object-realized datums on the heap. So in terms of consistency and scale, I said we're going to have two different decisions here, and we do, right? the processes and the writes go through the transactor, which means you have a traditional model for scalability. But two things are critically important. One, that transactor is not doing anything else. Right? All the read load, all the query load that a normal server would have been doing is gone. So usually, if you had 10-to-1 read to write activity, your server is now capable of 10 times as much work as it was before you did anything else. The other thing is that we have a full memory-driven model for transactions and a serialized model for transactions. So some great research done at Yale, which is the same research that's behind, say, VoltDB, which showed that if you take a traditional server and actually stop trying to do concurrent writes to the database, just say, forget it. You're all going to line up. We're going to get rid of all locking and all overlap logic and do everything in memory. It becomes 4 times as fast. So this thing is really, really fast. And so Datomic is for businesses for which that's going to be fast enough, and that's most businesses. The immutability supports consistent reads. And it means that those reads also do not have to be transactional anymore. So again, transaction processing is only for novelty. It's only for writes, update, whatever you want to think about, however you want to think about it. You don't need any reads, you don't need any transactions for consistent reads. And then the scaling of this on the most advanced systems, of which DynamoDB would be an example, on these storage services, it's just a knob. It's, how much read parallelism do you want is a knob on a system like that, which is really cool. And then the query part scales with the peers, and this part is truly elastic now. More peers, more query power, fewer peers, less query power, up and down during the course of the day. In particular, that kind of elasticity is dynamic, right? It's much different from saying, I know I need a cluster to do X, sometime, so I'm gonna enhance the size of my cluster. That is not elastic at all, and that's not very dynamic. You have to make big decisions. All right, we're going to go from 6 machines to 8 machines in the cluster. Being able to have query capability come and go triggered off of your sort of load detectors on the front end of your application is huge. It's huge because then it's not like you don't have a meeting about that, right? It's just in the middle of the day, there are a lot of people on your site and you need more query capability and you got it. Okay. So in terms of flexibility, we said we're going to represent everything as facts, entity, attribute, value, time. There's nothing to say about any of that except attribute. This is not a schema-less system. There's no such thing as a schema-less system. There are systems where you write your schema down and ones where you don't. Right? There's no such thing as a schema-less database. So we do require you to be explicit about this part of your database, which is what are your attributes? So any attribute has a name, it has a type, has a cardinality. Is this a one or a many? Right? It's really important to be able to say that, because if you can say that, the system can be smarter about it. It also does interesting things like say, is this a component of the thing that references it or not? In other words, is what I store here part of me or not, right? So your mother is not part of you, but your arm is part of you. And that really matters, right? Anybody trying to track those relationships in a deep tree to effectively remove an entity, it's really difficult, right? Cascading delete breaks down very quickly. So we make that explicit. Is it unique or not? And then we'll do the enforcement on that. And you can also give things identities so that you can use them as programmatic, like enumerators and things like that in your program. What you get, in addition to the fact-oriented view of the world and query against that, is also an entity-oriented view of the world where every entity is effectively a multi-map. It's like a Clojure map, except values can be, keys can point to multiple values, effectively to a set. So in terms of time, the database is a value, right? You can, that atom in there, when you dereference that atom, you get something that when you interact with it, you will never get a different answer ever. It doesn't matter what's happening as the system's moving forward, right? You dereference the atom, you get a value. It's exactly the Clojure state model, which means it's very easy to do multiple database queries. You can also ask a database, obviously you can grab the database at a point in time and hang on to it. And then time moves forward. And you can grab the database then and say, ooh, this and that. You can also go later and say, I have this database, I got the latest version. I'd like to see this as of last week. And you can get that value. But it's very important that getting that value is not a matter of issuing queries that include time as a parameter. Anybody ever try to write a system that manipulated time itself, yourself, right? Added a timestamp. Right? It's a nightmare. You end up with all these queries that have to flow timestamp through, and everybody has to use that timestamp correctly. And usually, you also in the same system need to provide some now view. And the queries that serve the timestamp and the queries that serve now are usually different, but they're similar, and they have to be maintained in parallel, and it's a nightmare. So when you say, I want the database as of this point in time, you just get another database value. You run the same query against that. You're querying last week. And you can say, since a point in time. You can also do speculative things, right? The database is a value. I can get this database value, and I can say, I wonder what this database would be like if I put this information in it. I'm not talking to this transactor right now. I have a value. I have stuff I'm thinking about doing. I want to see what that's like. That's all values. That's all right here. I can try that. So you can do speculative work, what-if work, validation work, all before you talk to the coordinated system to try to make it happen. And there's an optimization so that any pass that you've retracted moves to a separate index and therefore won't be in the way of now when you're trying to get that. I talked earlier about wanting to push novelty, so we do. The transactor pushes the transaction data, and you can just tap into it in an application peer, right? And just say, I want to hear about the novelty, and you'll be informed in a queue of the novelty, and it's just data. You can query that data. You also get past the database before and the database after. It's extremely cheap to make these two values. And that means you can make any decision. I mean, if you've ever tried to do this yourself with events or message queues, you always had the problem of, I sent you this message, now you know this happened, but the database has moved, and you need to make a decision that involves what happened and the database, but you really want that database, the one that's coordinated with this, not that one. Now it's straightforward, it's handed to you. So, I think you'll find that this is just, it's more of the same. Right? This is just the Clojure state model, finished. Incorporating time, incorporating durability, reifying process. It subsumes a huge portion of what you saw yesterday, right? Event systems, CQRS, logic programming, and all of that in a unified model. Right? You don't have to cobble this together for yourself. From an implementation standpoint, that dynamic merge is essential, right? If you encounter systems that say they do this, but they're like, oh, we append at the end with whatever, that does not work. That's never going to be fast, and it's going to be huge. You cannot do persistent data structures durably live, except with this two-phase thing. And, we keep hearing this, immutability is the key to this. This is an involved design with many pieces, but you could almost back into this design by just, taking a dose of immutability and seeing where it takes you. It's just following that all the way through. Implies a whole bunch of the rest of it. And whatever kind of system you're building, if you take that approach, if you say, I don't really know how to do this, but let's just start with everything's going to be immutable, and I really don't want to use atoms or refs except at the very end. You'll end up with better designs just by trying to follow it. So just do it. And that's it. Yeah, and of course after too, but any questions? Yeah. Yes?
What if you really need to delete something, let's say for legal reason, you can't keep user data for example?
Yeah, so because it's not updated in place doesn't mean that we can't do that. The question is, what if you have data you really need to make go away for legal reasons? Right? Your laws in your country say when the user doesn't want to be part of your service anymore, you have to nuke all their data. Right, so the easy way that's currently supported is just to retract it, but that's not sufficient for these legal requirements. So we will eventually support removing it, but again, that won't ever involve mutating something that already exists. And the way we'll accomplish that is by saying it's flagged for deletion, and the next index merge will not include it. And it will no longer be, and then those things will get garbage collected, and it will no longer be part of the database, but we won't have gone back to any segment and changed it. It's essential you really treat the storage as immutably as you treat everything else. Other questions? Yes?
Can the storage system be on each of the application nodes, for instance, if you had a key value store? For instance, Postgres, an instance of Postgres we have each node as well, or is it a single piece?
It could be. That's, you know, the good thing is that that's orthogonal. So you could do that as long as it made sense for you. One of the things is that those servers usually have different characteristics. Like most people now don't put a lot of storage on their application servers because they're just different kinds of machines and treated differently. Storage is usually you have to pay a lot more attention to a machine that's going to have storage on it than you would to an application peer. But you could definitely do it. Yes? Oh, we got? Last one. Yeah.
How do you synchronize the transactors?
You don't synchronize the transactors. There's no transactors, there's transactor.